I've been struggling all the day with that. I don't know why. Okay, so we have been discussing about many things. We have concentrated on the MapReduce model. Now, I think, as I said in the on Tuesday, you have a good basics of the experience with the design of the MapReduce solutions. As I said, we are going to move into more cluster-like environments when we will start working with Spark. But from now, I could say that you have these basics already in the pocket, so don't forget them. And before I continue with Spark, I wanted to wrap up a little bit to put into perspective what we have been doing in MapReduce. In fact, if you see, we have not been using any database management system. So if you have a general vision of what we have been doing in the course, is we started with storage problems. We showed some alternatives with respect to solutions that are very close to disk, but still are data management solutions. Then we get out of completely of the storage aspects and the data management aspects. We moved a little bit into some examples of data science problems in order to show that beyond storage and querying, there is another way of using and exploiting the data, which has to do with analytics, and that still the problem of defining the right operations in order to process data is an issue that has to be considered when we deal with data, and that, well, we have seen the classic setting today, which is you kind of forget about the storage, you suppose it solved, and then you concentrate on the data processing aspects, running your operations off the shelf of the data management system. Yet, if you have a database perspective, there are so many problems that if you do not use a data management system, that you have to consider in your programming practice. And when you have to deal with very simple examples as the ones we have been looking at, I don't know, median, max, statistics, etc. These are very simple. Even the inverted indexes and so on and so forth. These are kind of simple data processing problems that normally, without having the support of data management, you can still deal with them. Of course, because we are trying to think about scaling, but we do not have access really to problems and to data collections that would really put us on the limits of the architectures and the processing resources that we need. But when we scale, really scale, a question that comes into the table is whether not using a data management solution is reasonable for specific operations to handle. And in fact, this is not a novel questioning, okay? Many people think that when big data, the notion appeared and they came up with these new models and new data management systems, it was the first time that we as database community were thinking about the possibility of scaling through parallelization. In fact, parallel database systems have been around for a long, long time. Okay, so almost since there were more or less the second generation of data management systems, and we are talking about the 70s, when the first You know what is this? This is the alarm that our session was finishing, because we have 1 hour supplementary hour difference until Sunday, and my alarm thinks that that the session is finished, but it's not. So parallel solutions came into the table, as I said, more or less in the second generation of data management systems, quite a long time ago. And then when MapReduce emerged, and these new parallelization strategies, the community started to show again that parallel systems were there, that they still have to evolve, and the question is how they could evolve, okay? Why can't we use, first of all, parallel data management systems, particularly because at some point they tend to be costly, and they require a lot of expertise, and not everyone, not every company could afford the cost of buying one, managing one, and then having the right engineers that could do that, okay? And this is why it is important that you learn all these things, because this is the case again. Having people that know how to parallelize, how to run processes at scale is still rare. There's a market there, and this is why it is important that you have in mind that if you are preparing your professional life. So many people started thinking about this, and what I'm going to present is a motivational perspective. Okay, so it's just that, and the perspective is based on a discussion done by two main names, very important names in the database domain. One is David DeWitt, and the other one is Jim Gray. Jim Gray had the Turing Award, and then the story is a little bit weird, because he had a center, a database management center, a data lab funded by Microsoft, and then one day he disappeared, and so the center is still there, but the Jim Gray, nobody knows where he went. And so this discussion was there, and well, it's been around for some time. So what they put into the table was, why do we need parallel databases, or whether we really need parallel databases, or whether these out-of-the-box new solutions are enough in order to address data processing at scale. Then question is, if we do need parallel databases in any architecture that you can imagine, so you can even imagine that you go beyond the ANSYS Spark architecture, but if you still want to provide a data management system that deals with parallel processing, how would it look like? Then if you want to grab everything into a database system, which is parallel, how does it look like? And then other future research, future and open problems. It is important that even if we are in an undergraduate program, that you see open problems, because some open problems require fundamental science, but there are other open problems where it is possible that without doing rocket science, it's possible to address them, and then to find a market in existing companies, or if you are have entrepreneurship objectives and want to build a startup or something like that. So why parallel databases? Well, we still talk about relational data models, okay? Relational data models, everyone thought that in many moments of the history that they were leaving the arena, but they are still here, and data management systems have been evolving to keep up with new application requirements, and I believe that they will not disappear in at least in some time. So when you think about the relational model, in fact, the mathematical representation and characteristics of the relational model makes it a really nice candidate for parallelization, particularly because many reasoning and solutions that have been developed in parallel programming are dealing with matrices. And what is a relational table? Well, it is a matrix, okay? So its characteristics make it simple, as simple as it can to be good candidate to be processed in a parallel manner. And so if we manage to do that, there is also multiprocessor systems and that have become very cheap. I mean, I think that almost all of us in our computers, we have more than one node running in our PC. I mean, the PC that you get out of the chocolate box. Okay, so these computers already have multiprocessors, and so this is because now hardware has been democratized. Okay, so we have more power, we can scale, and we do not need essentially mainframes as long time ago in order to deal with important resources. Okay, then of course this discussion happened more or less when cloud computing was being democratized too. Okay, today, I mean, even if we need mainframes, we have them accessible on the cloud. Okay, but anyway, so this says that we have access to these resources, so we can imagine to develop parallel solutions at cost. And then the question is, okay, so we are happy, we can distribute the data, the tabular data across distributed architectures, we have resources, and then what does it mean and why would we need queries to be executed in parallel? And in fact, there are at least two properties of ideal parallelism that I haven't insisted enough with you, but that anyone must consider in order to decide whether you are doing good parallelism or just parallelism because of the sake of doing parallelism, but without really gaining something. Okay, so when we are playing and when we are learning, this is not a problem because the objective is that we learn, but if we are in a real setting, then we start caring about the time to market, person power invested in order to develop solutions, and also investment in the solutions that you will implement. And there you really have to make decisions whether to go parallel or not. Okay, and there are two like golden rules that help you decide whether you are doing good parallelism. And these are based in metrics. There are two metrics, the speed up and the scale up. And these two metrics have to be linear because of algorithmic reasons. And so linear speed up says that at n times large system yields to speed up of n. Okay, so if you have n processors, you have to go fast n times with respect to going in one processor. Okay, this is ideal. You never reach this because there is overhead in the interaction, in communication, etc. But this is what you are looking for. Okay, and then linear scale up that says that an n times larger system performs n times larger jobs in the same elapsed time as the original system. Okay, so this means that if we add processors, end processors, these end processors will be able to deal with jobs that are n times larger than an initial one. And then, well, you haven't studied parallel algorithmics, but theoretically, the parallel algorithmic community has shown that this is an ideal, but this is never possible. Okay, but again, you are trying to measure to which extent you are scaling up and to which extent you are speeding up. Because if you want your company to add new servers or add new processors in order that you can perform your jobs faster, you have to determine how many of these nodes your company is going to buy so that you can scale up, okay? And well, this is the basics of parallel programming. Then, of course, we in academia, we tend to question everything. And this is important because this is the way applied solutions also can move forward. The question is always whether these two indicators define good parallelism, particularly because it's their ideal and it's not possible to achieve them completely. In fact, what happens is that these two metrics are too general. And in fact, they can be specialized into two concepts. One is transactional scale-up, and the other is batch scale-up. And then transactional scale-up means that n times as many clients submit n times as many requests against an n times larger database. Okay, so you are trying to determine to which extent having more resources associated to your database or to your data management system, to which extent you can really deal with more requests, okay? Because as you know, well, that's something that you have experienced even in developing web applications. What is an easy way to hack a server? Well, you have a bot asking requests as crazy, and then at some point it can not longer deal with it. Puff, it breaks. Okay, so the idea is how much can I resist as a database system receiving requests and many requests, so n times many requests. And this has to do with how many transactions me as a data management system can face, okay? And then batch scale up means n time larger problem requires n time larger computers, okay? So these are the two parameters that could help better design whether we are doing good parallelism. Of course, remember that I'm always concentrating in jobs that have to deal with data, okay? It is possible to have another reasoning with jobs that do, of course, every job needs data, but not as we are thinking here, which is processing large amounts of data. And the question is always the same. Do we need to determine both metrics in order to profile the scale up of a system, a data management system, when we want to assess its performance? So in fact, people that have been analyzing the behavior of data management systems in order to make them more performant, etc., have looked, zooming into the problem, and in fact, they have seen that there are many barriers in order to achieve linear speed up and linear scale up. Okay, so it's not by adding resources as crazy that I'm going to achieve a better speed up or a better scale up, okay, and deal with more complex jobs. In fact, there are three elements that are barriers with respect to, well, they're not barriers, but they determine the performance of a data management system. First of all, startup. So the time needed to start a parallel operation dominates the total execution time. So if we go back to our MapReduce exercises, all the instructions that we considered in order to prepare the data, in order to organize them as key value pairs, etc., the story with the stop words, etc. All this is preparation, and it's done in the different nodes, but it's not part of the parallelism, okay? So this startup requires time, it's CPU cycles, and it stops it gets the speed up back, okay? And we never, or almost never, can get rid of that, okay? Even if we do not touch the data and that we really get the parameters already prepared, the problem of uploading the data and then that the process starts, the fact of getting the data from disk into memory, it requires time, and this is penalizing, and nobody can get rid of that. Okay, so this is one of the barriers, and of course you have understood that if we are dealing with a lot of volume, we cannot even have everything in one shot into memory. We need iterators in order to put everything in memory, and plus communication, and so this costs time and it's penalizing. Then interference. Slowdown occurs as new processes are added when accessing shared resources, okay? So that's something that we have seen empirically in the execution of our MapReduce programs. The fact of using the file system as common memory, shared memory, in order to exchange the data from the mapper and the reducer processes, or even from the towards the combiners, the partitioners, and then the reducers. This use of file system in order to exchange this data is of course penalizing. Okay, and besides this, sorry. Yeah. So besides this, the other problem is that there is the shuffling and the sorting. So all these interaction of the data among the different processes costs time, and so it penalizes both speed up and linear scale up. And then the third barrier is the skewness, which is a slowdown occurs when the variance exceeds the mean in job service times. So of course, we are not the managers, neither the dispatchers of the resources, but of course you have understood that if we are dealing with threads or we are dealing with processes, normally there is a dispatcher that, or the job tracker that is saying, okay, now everyone is finished, have you finished? All the mappers have finished, now then what's next? Do we start a combiner, not, etc. So all these coordination of the processes can cost time, and so if the variance exceeds the times, the execution of the time devoted to the execution of the job, then you have a barrier. Okay, so you should never invest more time in coordinating the processes than in executing the processes. Okay, so you need a performance manager, being the Hadoop engine or being the data management system, whatever system you are dealing with. This is important, and this is very difficult to ensure. Okay, and so this can First of all, we should be able to measure in order to determine how much it is being painful to the execution and whether we can reduce this. But in any case, this overhead can never disappear. Well, that's the general thing. And then all these barriers and these metrics problems, etc., are specialized depending on the parallel model and the parallel architecture that we are dealing with. So in the kind of parallelism that we have been studying, the idea is that our architecture consists of what we call shared nothing machines. I have insisted a lot when I describe the Hadoop engine that all the nodes composing the cluster are full-fledged servers, which means that they have their own disk, their own main memory, their own CPUs, or one or several, but their own processing elements, and they are independent, and their own operating system, and they are independent among each other. So this is a shared nothing machine. Okay, they contain everything they need in order to process jobs. And so in this type of setting, you still need to make these machines communicate, because they are going to work together for performing a specific task, no, a job. So the job is fragmented into tasks. We give a subtask to every server, and then at some point the results are synchronized in order to get the result of a whole job. No? And so in order to make them interact, that we have seen, there are at least 3 ways of solving the problem. The one that we have seen is shared disk. But there is also a possibility of sharing memory. So shared memory is all processors have equal access to a global memory and all disks. Okay, so instead of seeing the memory, the main memory of each server independently, the system will give the illusion that they have the same main memory. Okay, so every machine can see what is contained in the main memory of the others, because they only see one global main memory. Okay, so that is a way of making them collaborate. And of course, you can go further and say they do not only see the same global main memory, but they also see the several disks as one disk. Okay, so all the storage, sometimes including the cache, they see the summation of these resources as just one, and they interact with these spaces. Okay, so that's one setting. The other setting is that shared disk. So each processor has its own private memory. So my memory, you do not see what I'm thinking, but has equal access to all disks. So if at some point, this is more or less what we saw in MongoDB, okay? So if at some point I am full and I need to deal with a new fragment, then I can decide that I'm going to move part of the data that I had to another disk from another computer, and this is because the system has view to all the disks that compose the architecture. And then shared nothing, that's the complete really shared nothing machines, where each processor has its own private memory and disk. Okay, so that's the case of the Hadoop engine. Okay, the assumption is that nobody sees together, and it's only through the file system, which is an external element, that they can share results. Okay, but in between, nobody knows about the resources of the others. And so one question, okay, this is good for a solution like the Hadoop engine that we have seen, it works, etc., and it has more or less good results. The question is that, well, here the engine, the Hadoop engine, only concentrates on processing. Okay, there's nothing. It has nothing to do with other aspects of data management. Okay, it delegates this to the file system and or to an external data management system, but it doesn't care about managing the data behind. No. And the question is that if we do not want this, but if we really want to build a data management solution that takes care of the disk, that takes care of the way data are transported from disk into memory, going to cache, etc. So all these management processes that go beyond the file system. So the question is whether these shared nothing machines are reasonable architecture in order to propose a complete data management solution through a system. And so one important thing that this is the way I'm going to motivate toward Spark is that if you have a look at the programs that we have been designing in the MapReduce setting, what we design is, of course, functions. And then inside, of course, they deal with data, but the data are parameters. They are not exhibited as first-class citizens. And what we do is we define a control flow. The steps function that we defined using Python is a control flow. So it says, first you initialize the data, then you perform the map function, then you perform a combiner, then you can perform even a partitioner, then you reduce, and then you finish. Okay, so this is the job that we give to the job tracker, and then it parallelizes. Okay, so the data flow is hidden behind this control flow. Okay, and the control flow is sequential. That's the tricky part of the situation. And even if it's so the job tracker receives a sequential control flow, and then it distributes the different tasks, instances of the task, to the different workers that it coordinates. But the object, the general job is defined as a sequential set of operations. No? The difference when you think with respect to a data management system is that there is no control flow. In fact, what we have is a data flow. Okay, the execution plan of a query is in fact a data flow. It describes how data come from one node to the other, where the nodes represent operations, but the operations themselves are not important. What we know is which input is required in order an operator to work, and then what is the data that it produces that will serve as input to the next operator, etc. Sorry. So this is a main change, because we are not representing the control flow. And so models as MapReduce that are focusing on the control flow might not be well adapted when we only want to think about data, and particularly about queries, as we do in data management systems. So first of all, what we need to understand is, within a data flow, how can we insert parallelism? Okay, so relational data model operators take relations as input and produce relations as output. So that's the very first principle of a simple element of an execution plan. And then what happens is that we are going to compose the operators, and then we have a data flow graph, which represents the execution plan. And then what can be parallel is the operators. So what we need is to have parallel algorithms implementing the operators. Well, here we are talking about relational databases. So how do we implement parallel algorithms for every operator of the relational algebra, for example? So I'm going to parallelize the joins, the selections, the projections, the aggregations, everything will run in parallel. And then the data flow says just how these operators, how data flows across these operators. And so once you have this, well, an SQL query is, in order to answer the question, which says, how would you compose a set of operators for an SQL query to be done in parallel? Well, in the same way that would you do in a parallel manner, but the operators are parallel. Of course, you can go beyond this and you can partition the parallel, execution plan and try to perform it in parallel, but that's the second step. So you can have two levels of parallelization, in fact. What comes into the matter, which will lead us to the next part of the course, is either you have pipelined versus partitioned parallelism. So pipeline is the computation of one operator is done at the same time as another as data is streamed into the system. Okay, so if you imagine, let's imagine, what can we imagine? We can imagine fetch, and then you have two selections, and then the result of the selection, you compute a join, for example. So the execution plan looks like that. So you have data stream from two relations, let's say employees and department, and then the first operators are filters now. So let's say I'm interested in filtering employees with respect to their age. So I want employees between 30 and 55 years. And then here I'm going to ask for departments located in Mexico. And then I'm going to join them, and I'm going to produce employees between 30 and 55 years working in departments based in Mexico. Okay. So if you have this plan, what pipeline computation says is that the operator of the two filtering operators can be done, but can be executed in parallel. Okay, so I can have one node filtering my employees, one node filtering my departments, and then another node that will be waiting for the result of the other two nodes just to perform the join. So that would be a pipeline parallelism. So I'm going for a given execution plan, I'm going to design it such that I identify which are the independent operators that I can have in my execution plan. These independent operations will be executed in different nodes, and then the other operations will be executed either in one or several nodes, depending on the type of operator I have. So that's pipelined version. And then partitioned version is the same set of operations is performed on tuples partitioned across the disks. So this is more or less what we have seen in the map setting. I have, again, my filtering operation, filtering employees between 30 and 55 years. But what I'm going to do is I'm going to partition horizontally the table in as much nodes as I can use, let's say 3 nodes. So I partition my table horizontally, and I distribute the two tuples across different nodes, and then the filter is done on top of these subsets of my table, and then I can, for example, reduce them and do the union of that, for example. So that would be the two possibilities, and the question is, which one am I going to choose in order to develop a parallel querying solution? And you have guessed, we're going to combine both. Some issues about data partitioning. So if I choose to do this partitioned solution, here we are in the MapReduce setting that we have been studying the last weeks. Okay, so what is the issue with data partitioning? Well, there are, in fact, the issue is which is the strategy I'm going to adopt in order to partition the data. And there are, in fact, three strategies to be considered. One is round robin. For end processors, the ith tuple is assigned to the I mod end disk. Okay, so this is the way you are going to fragment your data. Okay, so instead of thinking about intervals, about hashing, or about semantic partitioning as well, fragmentation, as we saw in the MongoDB solution, you are going to reason in tuples, and then you are going to use this function in order to decide which tuple goes to the available disk that you have. Okay, and in that way, of course, you have guessed, you are going to have a balanced distribution of the data through the partitioning strategy. Then the other one, as you know already, so the hash partitioning, you have already tested this in MongoDB. In MongoDB, you were dealing with documents. Here in the relational solution, you would be dealing with tuples, and the tuples are assigned using a hashing function that it's applied to a subset of fields, for example, the key. Okay, so it's the same in the hash solution that we studied in MongoDB. You could decide to apply a hash function on top of the sharding key. So here the sharding key would exist always, but it would be representing a tuple. Okay, so it's exactly the same principle that you have already tested and discussed, and etc. And the range partitioning is the same as we have seen in MongoDB, but here we would be talking in terms of tuples, so clusters of tuples with similar attribute values on the same disk. For example, if we think that employees have an attribute age, we would say that employees between, I don't know, 20 and 25 years would go to a disk, the 26 to 35 to another, and then 35 to the oldest employee that we have in a third disk, for example. So the intervals, again, you know, and these attribute values represent the sharding key that you have already tested in the MongoDB solution. Then here, there are two important questions to bear in mind when you want to design a data partitioning strategy. Is what operations or situations are ideal or not ideal in order to choose this one of these three that you have already thought about in the case of MongoDB. So this is an important question, decision-making question that you as a designer of data partitioning strategies must bear in mind in order to develop a solution. So in your vademecum, that's one of the elements that you should have exhibited when you describe the aspects to consider in order to define a data sharding solution. So that's something that we have already studied. And then what issues to database performance may arise due to partitioning. This we touched a little bit when in the data, in the MongoDB sharding, and also when we studied the use of indexes and execution plan. This is why I insisted a lot in the exercise that you performed and the discussion to understand the importance of having access and studying the execution plan of queries. And then, well, we didn't go into the data partitioning, but at some point you discussed about how to observe whether we have a good data partitioning, and most of you said, well, I'm going to execute the queries and see whether they go faster or not, and this would tell me whether I have a good partitioning or not. So you're right, and this is the question that has to be considered. Of course, we are always looking for performance, at least. Okay, there are, remember the other two, consumption of memory and cost, that come into the arena, particularly when we are under pay-as-you-go settings. Do you have questions until here? A lot of information. Yes, please, Mauricio.
Yes, teacher. Well, first I have a question about pipeline. So
Yes.
pipeline is what I understood is that we have two operations that are expected an output to another input. Is what that?
You need to reason about the execution plan. So the execution plan is a well, in relational it is a tree, no? So if you see the execution plan, what you have, for example, in my example, you have the first selections of two relations at the bottom of the execution plan. So let's say that so that you can understand better. So my SQL, my query would be select all employees between 30 and 35 and 30 and 55 years old that are working in Mexico. So if you have this query, this means that you will have to join departments and employees and departments in Mexico and employees with 30 and 55 years old, and then join them, right?
Yes.
Okay, so if you have this query, this means that the execution plan would look like this. You would have two nodes at the bottom of the tree, one fetching, one selecting employees between 30 and 55, another node in the tree of the execution plan filtering departments by Mexico, and then a join that combines both results. If you have these three, since the two selections are independent, they have no data dependencies, you can decide that you execute them in parallel, meaning that you are going to execute them, well, the first selection in one node and the other in another node. And once you obtain the result, a third node can execute the join. So your operators are not parallelized. It is also dividing the execution plan and putting the different pieces of the execution plan to run in different nodes. That is pipeline.
Oh, okay, I see. Yes, I was just taking note.
You see?
Uh,
Yes, yes.
and okay, yes, I understood. Like
So here
we have a plan of execution, and we can see that there are
you always have an execution plan.
yes.
How to the problem is stated like this: how to divide the execution plan into portions that can be executed on different nodes.
Okay. So that
And
is
in the
what pipeline do,
partition,
no? Is
and then in
divide.
the partition is the opposite. How do I divide data such that the operations can be executed on the portions that I divided on different nodes?
Okay. And in pipeline we divide operations or data?
Yes,
The
operations. Well,
operation.
data too, because one employee, I mean, if you are going to node one, filtering employees, you are supposing that employees are also stored in node one.
Okay. And partitioning is a set, right? We have sets and we divide.
Partitioning is the data. How do I fragment my data
It's more set. Okay.
across the cluster?
Okay, I see now. Yes.
Right? Yes.
Yes. Thank you.
Perfect. You're welcome. Other questions? Now I realize some of you say that I speak fast, and today it's my day. I've been speaking like, oh, sorry. I will try to slow down. More questions? Okay. So that was, as you remember, one of the problems, the story of skew. That is somewhere back. Not going to go to back. Now, the other problem, so this is data partitioning. This is a problem that you have been working on, you know, etc. So that's something that you have already addressed. Now the skew problem. The skew problems we have not addressed a lot. So data skew is the number of tuples vary widely across the partitions. This part we have more or less seen because we discussed in the MongoDB sharding that if we used interval, for example, and our data were not distributed across, I mean, didn't have a nice bell distribution. So we could have partitions with a lot of data and others with few data. So if I have more employees between 30 and 55 and a very few between 55 and 65, the limit of work here, for example. So I would have a bunch of data in one node and very few data in the second node with employees between 55 and 65, for example. No? So this is data skew. And of course, you can imagine that this causes problems. Maybe when you have directed queries, not that much, but if you think about data processing, for example, if I want to do the statistics of, for example, just counting the number of employees that I have in my company, the cost of executing this metric in node 1 would be much higher than in node 2 because I have few people between 55 and 65 and a lot of people between 30 and 55. Okay, so that's the problem of skewness, and of course I have to avoid this as much as I can. And then execution skew says that due to data skew, since I have this like this, so more time is spent to execute an operation on partitions that contain larger numbers of tuples. So that's what I have explained. And the question is whether this skewness can be modified. Of course, in my toy examples, it is very easy to find a solution. But if you have tables with many different attributes, a lot of tables, etc. So the problem is an optimization problem, and it can be complex to decide what is the best strategy, because also you are not only going to answer one query, you are going to answer many different queries. So a partitioning can be interesting for a set of given queries, but very bad for other types of queries. And so you have to think about a balance. Today, people are applying artificial intelligence solutions in order to solve these decisions. But for the time being, in classic settings, this is a data administration problem. Okay, so there are groups of people working with statistics and making decisions on how to best distribute the data, solve skewness, so that you can have performance systems run. Okay, so this is a real problem related to a data solution. And then comes parallelization of relational operators. Imagine that, okay, I can have pipeline solutions in order to deal with my execution plan. So happy that I am. But what happens if I go further in these aspects, and I also parallelize the operators? So rather than writing new parallel operators, the idea is to use parallel streams of data to execute existing relational problems in parallel. Relational operators have a set of input ports and output ports, and so a parallel data flow is partitioning and merging the streams into the operator port. So this is before parallelizing the operator. So a simple way of parallelizing is what I have described in the pipeline solution. I'm going to work with the execution plan without bothering or revisiting the algorithms, but we wouldn't be happy if this was the only solution possible. So you will see later on that there are parallel algorithms for the operators in order to have the worst and the best of everything. Also, here we have a nice example with a nice plan. So, well, I have been working with queries. The thing is that when we manage databases, we do not only query, we also insert data, okay? So let's have a look at this. We want to insert into a table C the result of joining table A and B according to their attributes X and Y. So the execution plan would look as follows. So we would scan. Scan is an important operator that we never see in explicitly in the query, but in the execution plan we have to exhibit it. So we are going to scan the tuples from table A, which is this operator. Then we are going to scan the tuples of table B, which is this operator. Then we are going to perform a join out of X and Y values. And then since we want to insert, then the result will be inserted into table C, okay? So if we want to parallelize this nice, simple execution plan, we could, for example, parallelize, well, we would split B into several pieces and A into several pieces, and we could scan fragments of A. So I would fragment the relation A into several fragments horizontally, and then suppose that A1, A0, A1, and A2 are stored in different nodes, and so I would scan in parallel the fragments of table A. Then I would fragment, I can split be into this, and so I can fragment these two pieces of table B. But here I have 2 and here I have 3. Now I would like to perform the join. So the join could be performed by combining B0 with A0, B1 with A1, and then I get the result, and then I use the third partition with the result of these two in order to join the third part. Okay, so here is to show that the way you are going to partition the data will have an impact on the way you can pipeline the results and execute other operations, and that the operations, even if it's a join, you can still work on the pieces of combinations of your fragments in order to reproduce parallelization. And then again, with the different portions of your join, you could insert in fragments of C instead of just having one C. Okay. So the question is, who is going to build this strategy? And the answer is you. So you have to figure out of the an execution plan like this, how to rewrite your execution plan into a parallel pipeline execution plan. Okay, and of course there are rules, etc. In order to do that, you have to be acquainted of, but this would be out of this parallelization, rewriting the way your plan would look like, and then you execute. And so again, very important to bear in mind, of course, the difficulty of defining this parallel pipeline execution plan. But the very important thing to remember is the difference between the fact of having a data flow like this one, and with respect to the fact of having a control flow as we have seen in MapReduce. So that's the key issue. If you do not see it right now, do not worry, because the next part of the course, where we are going to study deeply these data flow stories, and we are going to test them on top of the platform Spark. But anyway, now just bear in mind this, but at some point I will notify you when you really have to make sure that you really make the difference between these two notions. And then the other aspect that that I'm not going to go through today and never, but that I want to insist on, is that beyond the pipeline solution, you can still decide how to execute this little thing in parallel. So imagine that this join, we have devoted nodes in order to execute our join in parallel, and we just use these devoted nodes in order to parallelize our join. And in fact, what you have to know is that these algorithms exist. Many of them, as we have seen in the MapReduce patterns, have been implemented as in a MapReduce pattern. And what is important for your culture to know is that almost all relational operators can be implemented in different ways. Okay, so an advanced knowledge of data management and data querying, etc., is knowing the principle of implementation of these, at least of the 5 fundamental operations of the relational algebra. Okay, so this is important that when you have time, get acquainted to the different implementations, because this is something that we should know. So regarding join, there are three main algorithms that have been proposed in order to implement join. Of course, you must know that even today I was attending EDBT conference, so there are people still trying to develop better join solutions in particular settings, but join is always a problem. So the algorithms that have the most popular ones to implement a join is the hash join. I'm not going to go into details today because we need a little bit of time to explain. I will profit from the transition into Spark to explain this in a thorough manner. So we have hash join, nested loop join, and these particular two have been implemented in parallel. Okay, so with many different versions, etc. We will see the MapReduce implementation and then how it is integrated in Spark. So that's part of the transition. And then just to finish the session today, let me see, what time is it? Yes. These strategies have been implemented in real systems, and these are parallel database systems. There are many well-known systems. If you go to companies to work, you might get acquainted to them. Teradata is one of the most important ones. It has still become very popular today. They are being installed. An affiliation of the Teradata is being installed nowadays in Mexico. So, well, now today they are dealing with data processing and data science things, etc. But Teradata is still a parallel database system, very well known. There's another one called Tandem Nonstop SQL. Gamma has been around and very important one. Super Database Computer, Buba. So all these names have been around for ages, and they are examples of parallel database systems. There are others that seem maybe more in the air of time. There is a MySQL cluster, for example, that is around, and that it's a parallel version of MySQL. So what else did I wanted to say? Yes, this, which will leave me in the starting point to go to data flow parallelization. So there have been many future directions and research problems. Again, when I say research, this doesn't mean that you have to go to master and PhD to address them. It is also possible to consider them and see whether you can come up with interesting solutions that can deal with cartridges or with extensions that can solve particular requirements and that can help you, for example, fund startups or cartridges that you can sell. So concurrent execution of simple complex queries. Okay, so that's a thing that have to be considered. Of course, when we talk about big data, and this is the topic of the course, we are talking about scale, etc. But there are very cute, simple problems that are still there and that can be addressed with scheduling and intelligent ways of dealing with the data. Parallel query optimization. So query optimization will always be an issue. Today, when we are combining classic relational-like operations with data processing coming from artificial intelligence and machine learning, so these new pipelines, as the one we saw in the notebooks, need optimization, need to be executed in parallel and need optimization. So this is an important thing to consider. and then application program parallelization. So you have, now you assume that your database is parallel and it runs perfectly and blah, but then you have the application. And the question is, in order that your application profits from all the power of the parallel solution that you have behind in the backend, you could imagine that your application is also aware of this parallelization and is designed such that it takes advantage of all this power, okay? And so this needs to be designed, and this is not very common, and this is a good market to address. Okay, so with this, I'm going to finish the session today. There's some minutes if you have questions, and then, as I said, tomorrow we will move into these data flow issues and start moving into Spark. Okay, so questions, comments. I'm going to stop sharing. Will you give us more time tomorrow activity? Yes, how much time do you need?